Okay, good morning. Welcome back. Till now, we have been discussing in the last couple of classes, we have been trying to develop a framework of dealing with nonlinear systems, and we saw that even though nonlinear systems are difficult to handle on their own, but if we perturb them with some incremental perturbation, then the relationship between the perturbed voltage and the current, regardless of wherever you have perturbed the circuit and wherever you are observed, can be modeled into a linear relationship, right? So that essentially gives us a handle of using all the methodologies of dealing with linear systems, LTI systems, linear algebra, set of linear equations, and so on, right? So once we are in that domain, life becomes easy. So a very quick recap of what we have been doing. So again, good old R and an element in the series. So this is VA, this is R. So this is an element which has a nonlinear IV characteristics. So I would refrain from using f of something from now on. Sometimes we'll have to use it, but the function gives a connotation that we are only dealing with maths. Sure, there is mathematics is a backbone of engineering. We'll use it, but I want you to get comfortable with dealing with everything with V and I, right? So when initially what we did was we said I equal to f of V, and we differentiated the function f dash, right? So essentially, what are we doing? We are essentially doing this. We are differentiating the I2V characteristics. If this is the I2V characteristics, and maybe you are somewhere over here, this is your V1, I1. By the way, what do I call this V1, I1 if after some numerical approximations I have figured out this is your V1, I1? What is the terminology that we use? Quiescent point or operating point, right? Fine. So now what we essentially said was that if I write the KVL of this loop, this becomes VA is equal to I1R plus V1. And then if we say that we have perturbed this loop with some delta VA, then I know that my current will be perturbed also by delta I1, and this voltage will also be perturbed, which will become V1 plus delta V1. And the relationship between the perturbations and the original voltage, or the operating point voltage, or the quiescent voltages and currents can be expressed in the form of KVL as follows. So VA plus delta VA will be equal to I1 plus delta I1 times R plus V1 plus delta V1. Now, what is delta V1? How can I make my life easy? If I want to express delta V1 in terms of delta I1, so again, I'll take you back to this graph, to this plot. When I say I am taking delta V1, what am I saying? This plot, in the IV characteristics plot, V is the dependent variable and I is the independent variable, right? But when you look at this network, and you are trying to figure out what is the dependent variable and what is the independent variable through this nonlinear element, can you make a comment? If the question is not clear, let me rephrase. What I am essentially saying is that if in order to get this plot, what do you need to do? This plot is independent of the network in which that a nonlinear element has been plugged in, right? So let's say you are in the lab, you want to get this plot. What will you do? You will simply take this element, apply a voltage source, across it and observe the current, right? And you change the voltage source and you observe how the current changes and you plot. And this is essentially the resultant of that plot. So when I am doing this experiment, I can say that V1 is an independent variable because I am changing it independently and I'm observing I1, right? So this plot is a result of some experiment that was done a priori to get the IV characteristics, where V1 was the independent variable and I1 was the dependent variable. Now I can as well turn around and do the reverse. I can say that I'll push in some current I and observe the voltage V. Right? I can as well do that. Then I will get an I2 V2I characteristics, right? So in that case, your axis will be this, right? So whether it is a dependent variable, whether I is a dependent variable or a V is a dependent variable is dependent on the experiment that you have done a priori. But note that whatever plot I will get between this and that will essentially be the inverse of each other, right? So it doesn't matter what, I mean, you are given I2V plot, I mean, you are given the plot on the left, or maybe you have given a plot where V is in the y-axis and I is in the x-axis, right? So the key point to note is that the tangent to the plot on the left will be equal to, if I take the tangent at this point, this tangent is del I1 del V1. If I draw a corresponding plot on the right, it probably will look something like I1, so it probably look. So the way I have drawn it, it becomes difficult to visualize. So let me draw it like this. So now if I draw the plot here, it will look somewhat like this, and the corresponding I1 V1, the tangent here will essentially be the inverse of the tangent that you got from the plot on the left, right? So here you are essentially getting del V1 del I1, right? And naturally this relationship between these two are reciprocal. Okay, so now can you comment on what is this quantity? What is the unit of this quantity del V1 del I1? Ohms, right? It's resistance. I mean, assuming everything is real, this is resistance, and naturally the tangent on that tangent of the I2V characteristics is conductance, right? So now when I have to replace this delta V1 with something which is corresponding to something proportional to delta I1, which quantity am I looking at? Which plot am I looking at? Am I looking at the plot on the left or the plot on the right? Plot on the right, because I am essentially trying to figure out how can I replace delta V1 with something times delta I1, right? So which means that I will, if you are given the plot on the left, doesn't matter. What you simply do is do reciprocal 1 of del I1 del V1 times del I1, right? And note that this quantity here, 1 over del I1, del V1, or simply del V1, del I1 is what we call an incremental resistance, right? So simply because it is relating your incremental current with an incremental voltage, right? So what is this quantity? What is this entire expression telling you? This entire expression is telling you that you have developed a voltage delta V, right? You have developed a voltage delta V when you have passed a current. Let's say you have a current source, delta I1, and you have passed it through a resistance of value 1 over del I1, del V1. Then the voltage across this is del V1. This expression is essentially telling you this, which essentially means that this del I1, del V1, 1 over del I1, del V1 is the incremental relationship that, or rather, it's the relationship that is relating the incremental increase of currents and voltages with each other in a proportionate manner. And from Ohm's law, we know that anything that relates I to V in a proportionate manner is either a conductance or a resistance, right? Depends on whether it's I to V or V to I. Okay? Make sense? Okay. Now, what you have to be careful here, this is some of the common mistakes that happen, is you will often see that in questions we'll ask you, find out the operating point, find out the incremental equivalent of this, find out the incremental equivalent of the circuit, and so on and so forth. So you will have to be careful. You have to be, initially when you are starting off, you have to be careful to discern whether we are asking for the absolute voltage or we are asking you for the incremental voltage, right? Because note that the incremental voltage will depend on the incremental model, right? So incremental model of a forward bias diode was a resistance, or rather is a resistance. So when I am asking you for an incremental voltage, you have to replace the diode with a resistance. But if I ask you for an absolute value of the voltage, then you have to take into account the operating point of the diode also. At that time, you cannot simply put a resistance, remove the diode and put a resistance, right? So to a quick recap is, we know how to deal with LTI systems, but when you are faced with nonlinear systems, what is the first step that you have to do? The first step is find the operating point. What is the second step? What is the second step? Find the incremental equivalent. That is, you have to replace the nonlinear elements with their incremental equivalents. And then do a linear analysis in the incremental circuit. And then what is the last step? If you have to find out the total voltage and the total current, at the operating point with the increment, right? So essentially what we are saying, the total voltage will be equal to operating point voltage plus incremental voltage. Or similarly, total current will be operating point current plus incremental current. Okay. So this essentially is what we have been doing for the last couple of classes. Any questions? Yes. Right. Okay. Good question. Good question. So what he is essentially saying is, if when I take a tangent line here, right? So if I take a tangent line here, this definitely doesn't pass through the origin, right? So this passes through somewhere here, right? But note that I am not bothered about that, because when I am doing an incremental picture, what is the relation? The relation is this. The relation is, where did I get? Okay, I removed it. What is the relation between the incremental change of delta V and delta I? It's simply y equal to mx, or del y equal to m del x. Right? The plus the terms goes away, because I am doing an incremental, I am trying to establish an incremental relation. Right? I mean, what you are essentially pointing out is, we have y equal to mx plus c, because if I simply draw a tangent and try to establish what is the equation of that straight line, it will be y equal to mx plus c, right? But we are not particularly bothered with the full equation of the straight line. We are bothered about the increments, because that's what we are after. So what we are doing essentially, we are saying that if y equal to mx plus c, what is the relation between del y and del x? Right? So this is perfect LTI. Right? Okay, good question. Thank you. Okay, so now I have been doing this in a very heuristic manner with some examples, because examples obviously help us in understanding the concepts better. But let me try to convince you of the same thing in a completely pictorial form. In pictorial, as in, when I say pictorial, I essentially mean that you try to use circuits, pictures as much, and equations as much lesser, right? Since you are more comfortable with equations as of now, so I started off with equations, but let's try to do the same thing using networks, solely networks. So let's take another circuit where you have two nonlinear elements. Okay, so you have, let's say, VA, your current through the loop is I1. This is, say, V1, this is V2. So this is V1 I1, this is V2 I2. Okay. So what were we doing? We essentially said that now, okay, so now if I have to, so note that here VA is equal to V1 plus V2. And since it's a single loop, we don't have to establish a relationship between I, because I is the same everywhere. So what I'll do is I'll just apply an incremental delta VA. Okay. So if I apply an incremental, let me draw a different network, so that will help make the point. So if I apply delta VA, the voltage across, the current through this will change. It will go from I1 plus delta I1. This will be again I1 plus delta I1. So this voltage will be V1 plus delta V1. This voltage will be V2 plus delta V2. So no harm done. I haven't changed anything. All everything is legal, right? So now, are you aware of substitution theorem? What is substitution theorem? Not really.
By current source or a voltage source.
Yeah. So what let me, if you don't know, let me quickly recap. So let's say you have a network. Let's say you have a network. Maybe it's driven by something, and you have a bunch of RLC, whatever inside. It need not be RLC. It can be any nonlinear element. You have some element, right? You have some element, and you observed that under certain condition, at steady state, the voltage across this is V, and the current through this is, let's say I call it VE, and the current through this is IE. So if I take this element out, right? If I take this element out and replace this with a voltage source of VE, will anything else change in the network? What do you think? So take this example, right? Here, I had a volt. Okay, so let it be here. So let's take the example of a known circuit, right? So you had this. You had this diode, let's see, a VD, VAR. You observe that the current through this loop is I1, and the voltage across the diode is VD, whatever the VD might be. Then in your experiment, you remove this diode and applied a voltage source, which gives you the exact same voltage VD. Will the current I1 change? No, right? So similarly, this argument can be, I mean, this is obviously not a rigorous proof. You can prove it rigorously, but the argument essentially is substitution theorem essentially tells you that you can replace any element in the network with either a voltage source or a current source corresponding to the original voltage or the original current before you did the replacement, and nothing else will change in the network. That should be also very intuitive, right? If I am preserving the voltage across an element, right, then the rest of the network doesn't have to bother, right? How is the voltage across an element affecting the rest of the network other than the fact that it is giving you that voltage drop, right? So if we can conserve the voltage drop across an element, then rest of the network shouldn't bother as far as solving KCL KVL is concerned, right? If you are solving the KVL, you are going around the loop, checking for voltage drops, and I am preserving the voltage drop by replacing an element with a voltage source, which corresponds to the voltage drop that it was originally giving. You don't seem convinced. Either, I mean, you are okay, or I mean, yes.
For example, in BJT, if we apply the voltage on the saturation region, but the current is still saturated, we can apply different voltages but will at the same saturation.
Okay, so firstly, I haven't come to BJT. When we come to BJT, we'll see. But essentially, what you are trying to say, so what you are essentially saying is, if let's say there is a sharp change in current or a sharp change in voltage, then what do I do? Right? It doesn't really matter, right? If there is a sharp change in voltage or current, whatever is even if it's a sharp change in current, you have a value of current. So you take that value of current and replace it. That's all you have to do. Because obviously, when you change an element, you are removing the element and plugging in a voltage source, or you're removing the element and plugging in a current source, then obviously that element has changed. There is no doubt. But the question we are asking is that does the rest of the circuit know that element has changed? Because how does the rest of the circuit interact with that element? It interacts with the current and voltage that is going through that element. If I am preserving that current and the voltages through that element, then the rest of the circuit doesn't bother, right? It's almost like a black box. And the current voltage relationship for that element is a black box for the rest of the circuit. If I can retain that, then I can as well replace it with anything, as long as rest of the circuit isn't bothered, because they are only interacting with that element through the current and voltage relationship. Okay, so that essentially is a story-wise storytelling of superposition, but obviously you can do a rigorous proof. So now, if you are convinced, what I'll do is I will replace this V1 plus delta V, right, with a voltage source of V1 and obviously an incremental delta V1. And nothing changes, right? Similarly, I will do the same thing for this chap, V2, delta V2. Okay. So now the issue is, by now you should be, you should think ahead, and you should be able to understand what I'm trying to do. I'm trying to establish a relationship between delta V and delta I pictorially. So, in this, I have V1, VA, V1, V2, I1 through the loop. So I have to cancel them somehow in order to get a pictorial relationship between delta V and delta I. Now, note that what is the relationship between VA, V1 and V2? VA equal to V1 plus V2 that we got from the previous network. So now these three collapse, right? This is VA minus V1 minus V2 if you go around the loop. So essentially what we are left with is this delta VA delta V1 and delta V2. And you have on top of that, you have currents of I1 plus delta I1. Here you have I1 plus delta I1. Here you have I1 plus delta I1. Okay. So now I have to get rid of the current I1 in order to establish a relationship. So how do I get rid of current I1? So if I add zero current to a node, right? In principle, if I add zero current to a node, I'm not doing anything, right? I'm not perturbing the circuit. Now, there are different ways of adding zero current, right? One might say, what do you mean by different ways of zero current? So I can push some current in and pull that equal current out, right? That is one way of adding a zero current. So what I can do is I will, at this node, I will let's say push some current I1 in, or rather, other way. I'm pushing some current I1 into that node, and I'm pulling some current I1 out of that node. You'll see. Okay. So essentially, I'm trying to get rid of I1 from the loop. Okay. So I'm pushing some current in and taking some current out. Essentially, I'm adding zero current, no harm done. I'll do the same thing at the other node. So this current anyway was coming out. So I'll push it in here, and I will pull an equivalent current I1 out. Okay. And the same thing I will do this here, right? So and the same thing I will do here. Okay. So now concentrate on any branch. Let's say I concentrate on this branch. Not the branch, this loop. So what do you see? You see that in this loop, or rather, what I observe is that if I redraw this loop separately, what I am seeing, or redraw that segment separately, what I'm seeing that I have delta V1 here, and I have this I1 plus delta I1 is flowing through this. And this I1 is across it. It seems like that, right? If I observe this loop. So now can you comment on what is coming out? What is the current that is coming out through these terminals? Only delta I1. So I1 goes off, right? So similar argument you can have for all these subloops. Do you follow? So if you have the similar argument for all these subloops, I can say that I1 goes off for all the subloops. So essentially what I am left with is delta VA, which was applied incremental. You have delta V1, you have delta V2, and the current through this is delta I1. Okay. Now, what is the relationship between delta V1 and delta I1 from all the stuff that we have done till now? If a current delta I1 is, if I have to use superposition again and replace this voltage source with some element, what element will I replace it with? A resistor of value? Delta, right. So I have to replace it with a value of resistor. I have to replace it with a value of del V1 by del I1. Similarly, I have to replace this one with a value of a resistor, delta V2 by delta I1, right? One second now. So if you do this, you see that you preserve the voltage drops across each of these elements, right? Question. Yes.
How can we say that the delta I1 is going to delta V1 or delta I1 is going only outside the loop?
Okay, good. So now what I can simply say that this I1, I can take out this I1 and say that this I1 is this. Now note that this is the voltage source, right? This is the voltage source. Now, I mean, you should have caught me here, or rather you should have asked me the question here that how can I now look at this loop, and see that there seems to be no resistance here also, right? But seems to be I have a whole bunch of voltage sources. In a loop, I don't have any resistance, but I have a whole bunch of current sources. Is that possible? In principle, it's not. But note that if you add up all the voltage sources, you get 0. So you essentially are in the 0 by 0 form. Right? When you have 0 by 0 form, something else determines what the quiescent states are, right? But since I have started from a quiescent state, the assumption is that, or not the assumption, you can argue that after you replace each of these elements, nothing else has changed. So now, essentially, it is a thought experiment. It is a thought experiment to show that if you have, if this is a black box, right? If this stuff that you are seeing is a black box, for the rest of the circuit, it really doesn't matter what is happening. Now, what I am trying to establish here is that how can I replace the black box with? By this argument, I am trying to show that you can replace this. Once you are into this incremental domain where you have delta V flowing through the element and delta V across the element and delta I flowing through the element, then it is equivalent to saying that if you know some delta I current flowing through it, replace that element with their incremental equivalent, which is delta V over delta I. Yes. Can you speak up a bit? Okay, so are you comfortable with this idea that so you're okay with this I1 plus delta I1, right? So now you treat this stuff as a black box. Right. So that black box got replaced here. Right. So when you replace that black box, what do you see? If you replace this black box, you see that whatever, and you are only observing the terminals, right? That's all you can do. You cannot really go inside the device. When you observe this terminal, you see you have across the terminal, you have a voltage of delta V1, current flowing into the terminal is delta I1. Right. So now you replace the black box. What for somebody who cannot go inside the device to figure out what it is, our only handle is I and V characteristics. And for a layman, for anybody looking from outside, it would seem like I have an element. If I put a voltage of delta V, I am getting a current of delta I through it, which in this parlance is essentially a resistor. Right. So essentially, what the purpose of this exercise is to tell you that you can come up with this incremental equivalence by purely doing some circuit jugglery, right? And you can replace any nonlinear equivalent with their incremental form simply because you can relate delta I with delta V through and across the nonlinear element with a linear relationship. Okay. Any questions? Yes.
Kind of loop. Where is it in the original circuit? This kind of black box. What is?
Oh, okay. So his question is this kind of black box, where is it in the original circuit? That black box essentially you can think of is this, right?
So in that what about the incremental circuit after you have yes, this one? How do you see this black box in that?
You mean in this circuit?
Yeah.
Okay. So to do that, I'll have to say that instead of tapping the I from there, I'll tap the I from here.
Okay. So I1 plus delta I comes in.
Right.
And I1.
Right. So it's basically redrawing the same thing. Okay. Okay. So I mean, obviously, I'm not going to ask you to prove all these things in your exams or assignments. The whole purpose of doing these things is to show you that we can come up with different circuit techniques or different conclusions through multiple routes. It's not as if only there is one route through which you can figure out what is we are trying to achieve. And one of my personal goals through this course is to show you or is to encourage you to think in terms of circuit equivalent, right? Maths is obviously will be there at the it's an analysis backbone, but since this is a circuit design course or the other circuit design and analysis course, I want you to appreciate circuit thinking or design thinking. Okay. Okay. So now there was one question. I'm not sure whether it was in the class or after the class, that how do we figure out what the operating point is if we don't have access to numerical? Yes.
Sir, in the source delta VA, we will be still having a current of I1 plus delta. Like either we have to replace it with a resistor, or you cannot put delta VA.
I didn't understand.
Like we cannot directly substitute delta VA as a final circuit because it is conducting I1 plus delta I. So to flow delta I1, we have to.
No. I see. This is fine. So what I understand what you are saying, but note that you are sitting here. You don't know what's going inside.
Yes, sir.
So if you consider this to be a black box and you put a voltmeter across it, what you will observe, and when you put a current ammeter through it, what will you observe?
But sir, where the current was went, which was associated with delta V.
That is still there. No. So this is there because you have this delta I1 here, right? only the I1 part gets cancelled.
Where is delta VA?
You have the delta VA. This is delta VA, right?
No, delta VA. Delta VA.
Okay. Okay, so you okay, delta V at this side. The same thing, same argument, isn't it? What I mean, you take any loop. I mean, everything is a.
You will take a look at you have to replace delta VA by resistance.
Okay. I understood your question. Okay, now, so his question is, what happens to, why didn't I replace this delta VA with a resistance? Is that the question?
Yes.
Okay. So the reason I didn't replace delta V with a resistance is because delta V by definition is an excitation. Right? Mathematically, yes, you can. Right? But in this case, the whole purpose of why we are having this delta I1, delta V1, delta V2 is because I have applied a delta VA as an excitation. So I cannot replace the delta VA with a resistance, and there is no source in the loop.
So how you deal with I1 as a delta VA?
Same thing, right? So you keep, so note that you, in this case, your current through delta VA is still delta I1. I am just not replacing delta VA by delta I. Replacing delta VA with delta VA by delta I. Because by definition it's a source. Right? Okay. So now so essentially what we are, I mean, the discussion that we are, thank you for bringing it up. So discussion that we are essentially having is, why didn't we replace this delta VA thing with the incremental equivalent, right? So now what is the incremental equivalent of a battery? I mean, we alluded to in the end of the last class, but what is the incremental equivalent of a battery? It's a short, because delta V by delta I for a battery is 0. So similarly, what will be the incremental equivalent of a current source? It will be open, because delta V by delta I will be infinity, right? So any current source you see, this incremental equivalent is open. Any voltage source you see, the incremental equivalent is 0, and that's essentially what I mean, that's essentially how you replace a voltage source or a current source. Okay. So quickly, I would like to do one more example. So one question came, I don't remember last class or the last before that how do I figure out what is the quiescent points, right? If we don't have access to, let's say in classroom, obviously you will be sitting and doing numerical approximations. How do I figure out what is the quiescent point? So I'll be posting an assignment today or tutorial today. There you will see some examples of you will see some examples like these. So let's assume that you have this nonlinear element. So if I ask you, or if the question asks you to figure out what is the quiescent points, rest assured that it will be something which can be hand calculated. Otherwise, there's no point, right? So let me give an example. So let's assume the I2V characteristics of this element. Let me call it Vn, In, that is nonlinear. The I2V characteristics of this is something like this, right? So let's assume if I assume this is piecewise linear. Piecewise linear, I mean that you can replace this curve with some line segments. This curve was probably originally didn't have any discontinuity, but to ensure that, I mean, at least to do some calculations, we replaced it with some piecewise linear equivalence, right? So, and let's say your R is equal to 1K, and I have this voltage equivalent to 1.5 volt. Okay. So now if I ask you, so everything is linear line segments. Now, if I ask you, what is the quiescent point of this circuit, or in other words, what is the quiescent Vn In? How will you go about doing this? Any thoughts? Adding the graphs. What do you mean by that?
If we will get a characteristic for working, then we will also draw the characteristic for the battery and where they will intersect. And we will add the voltages of the resistor and the IN's voltage.
Okay.
We will then see where.
Right. So
N plus R.
what he is pointing out to this is essentially we'll draw something called a load line. So don't bother with the jargon, but what he's essentially saying is that I know the current through this is some IN. If I can equate that current, if I basically apply a KCL at this node, right? If I apply a KCL at this node, what is the current that is flowing in? The current that is flowing in is 1.5 minus Vn by 1K, right? If I equate this current to Vn to In, then essentially I should get In, right? So this In equating can be done graphically also. You basically, what is this? What does this plot tell you? What does this equation tell you? It's a relationship between, so this In is equal to 1.5 minus Vn by 1K. So it's a relationship between In and Vn, which is also a straight line, right? With a negative slope, right? So you will probably be drawing it here and find out where these two intersect. Whatever these two intersect is your solution, right? So, but not mind it, this is exactly what you should do if you have access to graphs and everything else. But my question is, how do you know whether it intersects the steeper line or the lower line? Exactly, right? Exactly. That's what you have to do. You start off with the assumption. Let's assume that it intersects here, right? Let's assume that our operating point lies within this range, right? It lies somewhere between 1 and 2 volt and between 1 milliamps to 3 milliamps. And then you assume and solve. And if you assume that, what do you get? You get 1.5 minus Vn by 1K will be equal to this straight line. What is the equation of this straight line? You have the slope, you have the points. The equation of the straight line should be very easy, right? What is it? Okay, you can keep the millis in millis. Not only the slope, you need to, I need the exact line, right? Exact. I'm trying to figure, I'm not only here, I'm not figuring out the incremental equivalent. I'm trying to figure out the absolute voltage. So you cannot, the plus C term cannot be ignored, right? So what will be the equation of that straight line? Simple, right? So you have here, you know what is this? What is this? So your In will be 1 milliamps plus the slope. What is the slope? Slope is 2 milliamps by 1 volt, that is 2 millisiemens, times Vn minus 1, right? So this is, so essentially you replace this with, so what you get, 1.5 minus Vn is equal to 1 plus Vn minus 1. So 3 Vn is equal to 3.5, right? So Vn equal to 3.5 by 3, which definitely is more than 1, which means that did I make a mistake? What is 2.5? This is 2.5. Okay, 2.5. Okay. This is 2.5. Thank you. So Vn equal to 2.5 by 3. So which means the initial assumption is wrong, right? It was not here. It's not in this segment. It's in this segment. Then you rewrite the equation of that segment and solve again. Right? Make sense? Okay, fine. So I'll be posting the tutorial today. You'll have some practice problems on this. The next, we'll have a mini quiz next tutorial day, and it will be based on the practice problem that I'll be providing. Okay.